Hello and welcome to EE233. I'm your instructor, Gregory Myers. In this video, we're going to take a further look at the switches needed to be able to power our physics demo. In the previous video, I had focused in on setting up the initial switch structure for the 1D, 2D, and beam, and focused a little bit on the version 1 of the functions. We also counted up the number of arguments needed for each possibility, and then I laid out the 1D switches in full. And I ask that you continue with the 2D and the beam. What I'm starting off with in this video is that structure. And so you'll note that I have triaged effectively all of the 2D possibilities for versions 1, 2, 3, and 4. Notice that version 1 doesn't have either the interactive or the parametric possibilities because it simply collects the information inside the function. So in other words, it has to have a scanf, a printf, and a scanf. The interactive requires a printf and a scanf, which we will do in just a second. The parametrics capture the information from the command line. I've also done the same now for the beam. The last thing to note that we did not address in the previous video was what happens if the user enters in some combination that doesn't make any sense. In other words, doesn't trigger any of these combinations. And that should result then in us hitting this else, in which case we simply want to call the help that we should also have been working on or also expanding. And so we'll come back to the help in a later video. And the last thing to note is that this is not the only if structure that will work. As a matter of fact, in another video, I'm going to show you a nested if structure that could also solve this problem. I've just opted for this more flat structure because it's probably more approachable for the first time through in a project as significant or as large as this. So without further ado, let's get started now. And so we're going to focus in on the 2D example. And in the 2D example, version 2/I, we are going to have to collect from the user two pieces of information, because remember, this is two-dimensional motion. We need to capture the v init and the theta. So the first thing that we want to do is we want to have a printf that says, please enter a velocity. And once again, we're going to try to be as helpful as possible. We're going to say feet per second. We're going to give them the units followed by a slash colon and then a slash n. We also want to follow this up with a scanf where we collect the percent LF. And we want to store it then in our v init variable, and specifically at the address of our v init variable. The second piece of information that we need to get from the user is going to be the theta. So please enter an angle. And we can emphasize to the user that this needs to be in radians. And once again, a scanf with percent LF and the address of our theta variable. From there, then, it simply means that we need to call the projectile, in this case, version 2D, version 2, and to that function, we are going to pass our v init and our theta. Now, if we recall from an earlier video, we said that the function is not, version 2 of this function, rather, is not going to collect the information, but it is going to be responsible for printing out the table. So the only thing that we have to do here now is provide it with the information. So we need to have these printfs and the scanfs, and then we're going to pass it to the projectile 2D version 2, which is going to be responsible then for printing out the table. Now, for the 2D version 2 parametric mode, notice that the argument count has now jumped to 6. In other words, we're expecting those 2 additional arguments, the v init and the theta, to be on the command line. So we're going to end up using, once again, our a to f function to convert. So the first step then is going to be to say v init is equal to the a to f of our argv, and now we need to think about this for a second. So if argv3 is /p, then argv4 should hopefully be our v initial, and the theta should be then equal to our arg conversion of our argv square brackets 5, at which point then we can simply once again call our projectile 2D version 2, and we simply pass to it our v init and our theta. Once again, the responsibility for printing out the table is inside of the function, so we don't have anything further to do. That luxury is now gone when we look at the 2D version 3, and we're going to focus first on the interactive and then the parametric mode. What we can do now is we can borrow a little bit of our code, because in the 2D version 3 interactive, we still need to collect the 2 pieces of information. Nothing has changed there. The big difference, however, is that we are going to call now projectile 2D version 3, and we're going to pass to it the v init, the theta, and then we're going to pass to it the address of our t final, the address of our y final, the address of our vy final, the address of our x final, which is the total distance that the object traveled in the x direction, and then lastly our vx final. Now, remember that the responsibility now for printing out this table falls back on the calling function. So that means that now we need to print the table. Once again, we can go back to an earlier video. We can also go to this notepad that we have simply captured then the contents of our earlier main, and we will find here where we've called our projectile 2D version 3, and you'll see that we now have our nice table already made for us, in which case what we need to do is just simply paste it then into our main once again. Now, that gets us through our 2D version 3 interactive. Let's focus on our 2D version 3 parametric. And in this case, the 2 arguments, the v init and the theta, are assumed to be captured from the command line. Well, likewise from earlier, what we can do is we can simply come up here. We can copy the code from the previous example for the 2D and paste it. This is just simply the code that converts our command line arguments into the numeric equivalent. So in other words, this just converts a string into a double. And then once we've made our call to projectile 2D version 3, we simply print out the table. And as I mentioned in the previous video, there is a little bit of redundancy in this particular example, and that's perfectly fine. We're gonna look at how we can improve our code later, but for right now, we're just going to accept this a little bit of redundancy between some of our branches of our if statements. Now, moving on then to the last example for the 2D projectile, we're looking at version 4 in the interactive, which has then the additional requirement of capturing n, or the number of data points that we wish to return. So The first thing that we want to do is we can come up here to our interactive. We can actually copy the code that we have from earlier. And then we want to provide an additional prompt here. So it's going to be printf, please enter the number of points followed by a scanf where we capture %d, and we use the address then of n. Now note, we'll address this later. Right now, we're not going to focus on the dynamic creation of these vectors. And so what I'm going to do is just temporarily hard code n equal to 11 to match what we have declared our vectors to be. And once again, we'll cover this in another video. So I'm going to put another little note here. It says note, remove later. But from there, then, what we want to do is we want to reach back to our earlier example on the previous video where we ran the function, the projectile 2D version 4, and we passed it the v init, the theta, the time, the y time, and so on as vectors this time. So our projectile 2D version 4 accepts a v init, which is a single value, a theta, which is a single value, and then the vectors of time, y time, vy time, x as a function of time, and then vx time, as well as n, which tells us how many values are in each one of those vectors. From there, we can reach back to the code that printed out these values and simply, once again, borrow these two tables. The one table printed all of our, essentially our end values, the beginning end, the t init, the v init, theta, and the t final and y final, and so on. But then also printed the value at each index. So we want to go ahead and grab this table that we spent some time on earlier, go ahead and copy, and I'll paste it into our branch here of our if statement. We're going to have to tab it over real quick just to get it in line. And that's how we handle then our 2D/V4/I. So in our interactive mode of our 2D version 4 of our physics equation. Now, moving on to the parametric mode, it's very similar to the previous example. As a matter of fact, we can scroll up, we can grab a little bit of our code here where we converted using the A2F, the argv4 and argv5. But now we have an additional argument to worry about, and that is the n, and that is going to be converted using our A to I, and specifically it's going to be the conversion of our argv6. Now, as I mentioned just a few minutes ago, we are not going to worry yet about dynamically creating our arrays. So if anything, I'm just going to hard code n equal to 11. And I'm going to put a little note in here that need to remove later. We will handle that once again in another video. From here, then, there is really no difference between how you would deal with this interactively or parametrically. So at this point, you can simply copy the table down to this branch of your if statement. At this point, we are done with our projectile 2D. Now, for the last part here, what we want to do is we want to focus on the beam. Particularly, we want to focus in on the version 2, 3, and 4, and looking at the interactive and parametric modes for each. Now, for the interactive mode, of the beam problem, we still only require 4 arguments, because essentially what we're going to do is we're going to capture all of that information from the user. And so basically what we need to do is we need to prompt the user, potentially in the order in which we plan to pass the values to the function. So my suggestion, just for convenience sake, would be that we prompt them first with the W, the loads, the length, and then the location of the load. So we'll have 3 prompts here. We'll start off with a printf, please enter the load. And we said that we're going to keep this in pounds. And then follow this up with a scanf. So again, %lf. And we're going to use the address of W. Then we want to prompt the user using a printf to please enter the beam length. And the beam length for us is going to be in feet. And then follow that up with a scanf, once again, %lf. And the ampersand L. These are all scalar values here. Then the third one is going to be the location of the load. So please enter the location of the load. And that is also going to be in feet, followed by a scanf using a %lf and ampersand A. Now, at this point, we need to at least make a comment here that says that we would technically want to make sure that our A is not greater than our L or less than 0, because that would mean that the load is not sitting on the beam. So we do need to handle that and perhaps re-prompt the user. But once again, we're going to leave that for another video. Instead, what we're going to do is we're going to now make a call to our simply supported beam version 2. And we're going to pass to it a W, the L, and the A. And as was the case in our version 2 of our projectile problems, we are leaving the responsibility of printing the output to the function. So the only thing that we needed to do interactively was to capture the information from the user. Now looking at the beam version 2, the parametric version, the one that accepts the arguments from the command line, we are going to be looking at grabbing the load W, the L, length of the beam, and the A, location of the load, all from the command line. In which case then we simply say W is going to be equal to A to F of our argv. And now we want to think about this. Our argv3 is the /p parameter. So our argv4 ideally would be then the load. Our argv5 should be our length of the beam, and the A to F of our argv6 should be, in fact, our location of the load. From there, we simply make a call, much like we did in the earlier branch, to the simply supported beam version 2, passing the W, the L, and the A. Which brings us now to version 3. Version 3, the main difference is that in the interactive mode, we are collecting the information from the user, but it's also going to be the responsibility of the calling function to print out the table. And so in this particular case, we can actually borrow the code from our previous branch, our interactive branch, And then what we will do is we will make a call to our simply supported beam version 3. We're going to pass to it our W, which is going to be a single value, the L, which is going to be a single value, and the A, all of those by value. And we want to also pass to this function a reaction force 1, R1, but we're going to do that by reference as well as a reaction force 2, or R2, by reference. So in both cases there, we're going to use the address of operator. And then it is now our responsibility to print out the table, in which case we can once again go over to the notepad file that we utilized earlier. And we had already printed out this table. One second. So there is the table that includes the static values. Give me just a second. Copy and paste it here. Scalar values rather, not static values. And it appears as if we made one little change here, which we're actually going to comment out. And then you'll see that we have our nice table here. Prints out the L, the W, the A. And I believe we said that we wanted to keep this consistent here. So we're actually going to print the W before the L and the A. Once again, we might have done this a little bit different in another video. That's perfectly fine. All right. Now, that gets us through the interactive version. Now let's focus on the parametric version, or the one that gets it from the command line. And as we said earlier, what we can do is we can capture the W using the A to F of our arg V square brackets 4. The L is going to simply come from A to F of the arg V square brackets 5. In other words, the fifth argument converted from a string into a double. And then lastly, the A, which we're also going to convert using arg V6. And from there, we can simply call the simply supported beam version 3 and print out the table. So there's nothing functionally different here once we have collected the arguments from the command line. Yes, once again, there is some redundancy in this code. We could handle this a couple of different ways as far as printing out the values. But in this particular case, we want to focus first on the triaging of the switches. Okay, then we can optimize the code in a later video. Now, for the last one. And the last one presents a couple of interesting challenges. Because we can provide it a vector of weights and a vector of locations, we need to be able to create those vectors first. And essentially what you have is you have a load function and a location function. Now, in this particular case, I'm going to make some assumptions. I'm going to make an assumption that it is a evenly distributed load, not a point load, but actually a distributed load. And the W is actually going to be whatever that distributed load is. And I'm going to evenly distribute it using the N, or the number of points that the user is going to be asked to provide. Okay, so essentially, whereas in the first example, we had a 100-pound load at a single A, we will have a 100-pound load at multiple A's. In a later video, I'll show you then how you can actually provide a different type of loading. But for this example, we're going to essentially ask the user to provide first, so printf, please enter the load, and we're going to go ahead and provide it here. So this is going to be in pounds. And if anything, if we want to emphasize here, it's going to be the distributed load. And then scanf %LF. And this is once again going to be ampersand W. And then the printf, please enter the length. Keep consistent here. The beam length. Feet. Scanf with a %LF. And once again, our ampersand L. And then printf, please enter the number of points. Notice how I am not asking for an A here. And instead, I'm going to simply say %D and ampersand N. And as with the earlier examples, note we will address this later. And I'm simply going to follow this up by hard coding the N. Okay? So need to remove. Now, how are we going to do this? Okay, so basically what we're given is a beam L. We're told the number of points. So what we need to do is we need to create an array for the weights. And to do that, we're going to leverage our index variables. So for index equals 0, index less than n, index plus plus. And what we're going to do is we're going to create a W array or a weight array utilizing that index variable. And we're simply going to create, in this case, a 1 by 11 vector of weights all equal to W. The second thing we're going to do is we're going to need to create a position vector utilizing our A, in which case then we want to have then an A delta. These are both variables. All three of these variables, by the way, were already declared in an earlier video. And our A delta is going to simply be equal to the length of the beam divided by n minus 1 data points. So in other words, if you have 11 data points, you want to have 10 intervals. So it's going to be n minus 1, in which case then our A array, square brackets index, is going to simply be equal to the index times our A delta. And once again, for a better understanding of these computations and these values, please refer back to the earlier video. From there, then, what we need to do is we simply need to call our simply supported beam version 4. And we're going to pass to it our W array. We're going to pass to it our L because it is a single value, a constant. We're going to pass to it our position array, in other words, the location of each one of our W's. And then by reference, we are going to pass two other vectors, a R1 vector or R1 array, followed by our R2 array, and then the number of data points in each. At this point, since our function has no responsibility for presenting the data after we calculate it, we need to print the table. And once again, we can go back to our previous example where we actually went ahead and did a couple of things here. We printed out not only the values for the W, L, A, R1, and R2 at a given location or index, but we also summed up our R1 and R2. And so what that allowed for us to do is that actually allowed for us to know what the total reaction forces were given to a distributed load. We're just going to go ahead and copy all of this here from our previous example. Once again, I encourage you to go back to the earlier video. Paste this in here. We're going to tab this over just to keep it in line, which then brings us to our very last possibility, that is the /beam/v4, but more importantly, the parametric mode. Okay, and so note from the command line, the decision was made in the earlier video that we would not ask the user to enter in the A, but instead we were essentially calculating a distributed load. So the first value, the W, is actually going to be your point load, your original point load, which is going to be now distributed among several locations. All right, so it's going to be argv, or A to F, of our argv square brackets 4. Our L, which is going to be A to F of argv square brackets 5. And then the N, which is going to be equal to A to I of our argv square brackets 6. Now, from here, what we want to do is we want to once again construct, using n equals to 11, our A delta. We want to construct our weight array and our loading array and our location array. So essentially, all of the code from the previous branch can once again get copied down. And once again, just make sure that you have your call to your simply supported beam function. Now, I would like to take just a second to note that one of the things you can do, just as a slight variation on this theme, is that you can actually assume that W is the total load, in which case you could actually calculate this as W divided by N. All right, which would essentially mean that your weight was applied, the total weight was W, was what was captured from the user. So either version of this is perfectly fine. Okay, doesn't really matter which one of the two you want to do. We're going to come back and we can take a look at the loads later. All right, so I'm going to go ahead and build this to make sure that we don't have any errors, and then we can test it out on the command line. So real quick, before we do get to the command line, let's take just a second to clean up just a couple of things. Number one is going to be up here in our 2D table, and in our 1D table, we did not actually specify units. That would be probably a nice thing to do. So let's take a second here to include the units. So the velocity is going to be in feet per second. The theta is going to be in radians. Our T final is going to be in seconds. Our Y init is going to be in feet. Our Y final is going to be in feet. Let's see, what did we do down here? Yeah, we used parentheses and a colon, so we can take it just a second just to go ahead and colons after each one of these. Once again, it's just more for aesthetics, but makes it look like we spent some time on our application here. Our VY init is going to be in feet per second. Our VY final is also going to be in feet per second. Our X init is going to be in feet. And our X final is going to be in feet. Our Vx final is also going to be in feet per second. And our Vx final is going to be in feet per second. All right, now from there, then you can also put the units in up here in the column headers. There is, of course, no units for your index. There will be for your time. For your X time is going to be in feet. Our Vx time is going to be in feet per second. Our y as a function of time is going to be in feet. And then lastly, our Vy time is also going to be in feet per second. So if you've spent this much time cleaning up your table, you should probably go ahead and take a second to duplicate it rather than re-type that. And so you can come up here. We're going to overwrite previous version of the table. Obviously, take some care. Make sure not to overwrite something that you didn't mean to overwrite. And then likewise here, we want to go through and we want to carefully put our units in here. We can't just copy and paste blindly on this one because of the fact that this table is just a little bit different. So we'll have to do this one manually. All right, so we have our V init, which is going to be in feet per second. Our theta, which is going to be in radians. And our T final in seconds. Our Y init, which is going to be in feet. Our Y final, also in feet. Our Vy final is going to be in feet per second. Vy init rather. Our Vy final is going to also be in feet per second. Our X init is in feet. Our X final is in feet. Vx init, feet per second. And then lastly, the Vx final, which will be in feet per second. And likewise, if you've spent this amount of time, go ahead and copy and paste this table above. All right, so we have a few more that we need to do here. So we have our Y init, which is in feet, our Y final, which is in feet, T init in seconds, T final in seconds, our Vy final, Vy init rather, and our Vy final. And both of those are in seconds. And then we also can copy and paste this table. We can also include in here then the time, or Y time, and our Vy time. So let's see if we can copy, paste this up here. Let's make sure that we didn't miss anything. I don't think we missed anything on this one. Nope, I think we've got everything. We might have to come back and clean some things up, but you can probably do this on your own once you see what we're trying to do here. up here on the projectile 1D version 3, we have our y init, which is in feet, our y final, t init, t final, there we go. And then once again, go ahead and bring this up here. The rest of them are handled inside the functions, so we'll need to quickly chase those down. What you can do is you can go into your projectile version 1D version 2 and also do the same thing as far as improving your table. Feet per second. All right, and then if you recall, this is essentially the same table that was used in our version 1, and the same was used in our version 2. There was really no difference between the two. And at this point then, the table here for the 2D version 1, so it's going to be seconds. Data is going to be in radians, T final seconds, Y init is going to be in feet, Y final is going to be in feet, VY init feet per second, VY final feet per second, X init is going to be in feet, X final is going to be in feet, VX init is going to be in feet per second, and VX final is going to be in feet per second. And once again, this is essentially the same table that you have in version 2. All right, so then the last thing that we want to do then is going to be down here in the simply supported beam version 1 to keep consistent with what we did earlier. We said that we wanted to have the W first to keep in line with the other examples. So we collect the W, the L, and the A in that order. So we're going to just rearrange these. So nothing major there. And we're going to go ahead and readjust the table then here. So it's going to be W first, then L, and then A. And once again, this was a little different in an earlier video. It's not a big deal. And then the last thing I wanted to show you is that I completed out the help because we will need that when we're actually testing our executable, because we want to see our examples. And so you can see how many different possibilities we've got to test. All right, so I'm going to go up to main, see if we've got any other issues, any formatting issues or anything like that. And then we will get started on testing it from the command line. All right, we'll build it. And we'll come over here to the command line. And once again, you'll see that I'm in my physics demo directory. There is my physicsdemo.exe. And what we want to do is we want to just run through a couple of the cases here. So we're going to start off with our physicsdemo.exe, no switches, and you'll see that it calls help. Okay, so basically now you can think about our main and how we're triaging it. If argc is not 3 or more, in other words, if it's not greater than 2, then you have a problem. So we wrote it such that if our argc is less than 3, then we should display the help. And so even if I were to put something here, okay, it would show as argv1, and there's 2 arguments, but it would be not enough to trigger any of our functions. And so what we want to do now is want to go through some of our examples here. And I'm going to start with the 1D problems. And I'm going to move through. I'm going to focus on the 1D version 1 and version 2. And I'll do the version 1 and version 2 of each of these, and I'll leave the rest of them for you to test. So we'll start off. We're going to look at the 1D version 1. And that's supposed to be interactive, and so it's going to please enter the Y in it. I can see a place right there that we probably want to go ahead and add a unit. But there's our nice table. So that one seems to be working correctly. Let's try our version 2. Oh, wait a second. If you notice, we didn't provide whether we wanted to do it interactively or parametrically. So let's rerun that. We'll do it with interactive first. Please enter a height. All right. Same table as before. Now let's do it parametrically. Once again, we get the help. Why do we get the help? Well, because parametric requires that we actually provide the argument on the command line. And you can see, there we go. There's our nice tables. That one seems to be working correctly. Let's repeat this now with our 2D. And we're going to start off with version 1. It's going to ask us for our V init. There's another example of where we probably want to add some units. And the theta, same there. We probably want to add some units there. But once again, there's our nice table, nicely formatted. Now let's take a look at our /2D version 2. We already know what's going to happen if we don't provide an argument for the parametric or interactive mode. So we'll start off with /I. Here we are prompted with the units. And so we can also provide 0.785 for the angle. And there we go. You get your nice output. /P without the providing those arguments gets us the help. And so what we can do is we can provide the initial velocity followed by 0.785 for theta. And once again, there we go. We've got a nice table. So looking good so far. We want to move on now to our beam. And we're going to start with version 1, which is completely interactive. So enter in the load in pounds. Make it 100. The length of the beam is 10. And the location of the load is 6. So sure enough, it gets us our table. We're now going to do version 2 without specifying whether it's interactive or parametric. That should also get us the help. And so version 2/I is going to be interactive. Once again, enter in the load, enter in the beam length of 10, and the location of the load, which is 6. And once again, we get our nice table. And then lastly, if we enter in parametric, but without providing the argument, then we get the help once again. In this case, if you look here at the instructions, it tells you for version 2, you need to provide 3 additional arguments. So we'll provide the 100, the 10, and a 6. And sure enough, it does work for you. So hopefully you found this video useful. I appear to have a few things that I need to tidy up in my tables and add a few units here and there, but essentially you can consider this project completely done. Now, in another video, I'm going to show you how to move the code into a library. I'm also going to, in a separate video, show you an alternate nesting structure for your switches so that you can feel more comfortable using nested if statements. But essentially from here on out, we're going to be tidying things up. I'm also going to show you in another video how to do dynamic memory allocation that will allow for us to actually successfully use our N value. So right now we said we've hard coded these 11s in there. All right, so once again, hopefully you found this video useful. As always, if you've got any questions or comments, feel free to email me. Thank you very much.